The second law of thermodynamics. The second law of thermodynamics is a general principle which places constraints upon the direction of heat transfer and the attainable efficiencies of heat engines. Therefore, before discussing the second law of thermodynamics, we will remember a little about the operation of a thermal machine and the Carnot cycle. If you don't know the first law of thermodynamics, thermal machine, and the Carnot cycle, you should refer to this video. Thanks for watching this video, and don't forget to like, subscribe to the channel, and activate the notifications. It's very important to the continuity of this channel. A heat engine is a device that converts heat into work. A classic example is the steam engine, whose basic elements are illustrated in the diagram. Some form of fuel, oil, wood, coal, is used to vaporize water in the boiler. The vapor expands and does work against the piston. The vapor condenses back into water again, and the cycle repeats. The next diagram is a simplified diagram of a heat engine, along with its thermal cycle. The most efficient cycle possible is the Carnot cycle. In other words, the maximum amount of work that can be achieved by a thermodynamic exchange between two specific temperatures is given by the Carnot efficiency. This efficiency of a heat engine can be written as follows. Since the amount of heat depends on the temperature, the ratio of the temperatures must be the same as the ratio of the transferred heat. Therefore, the maximum efficiency of a heat engine can be rewritten as follows. Now let's look at that last equation. This is the equation for the maximum efficiency of a heat engine. Suppose for a moment that we could construct an ideal engine, perfectly reversible and free from all forms of friction. Would this ideal engine have 100% efficiency? No, it would not. To achieve 100% efficiency, the cold reservoir would be at absolute zero, and it's not possible. Let's look at this equation again. If the hot and cold reservoirs have the same temperature, so that it follows that the maximum efficiency is zero. As a result, the amount of work that such an engine can do is also zero. Therefore, a heat engine requires different temperatures in order to operate. From these observations came the second law of thermodynamics. The second law of thermodynamics states that it's impossible to have a cyclic, repetitive process that completely converts heat into work. It's also impossible to have a process that spontaneously transfers heat from cold objects to hot objects. The first part of the law says no reaction is 100% efficient. Some amount of energy in a reaction is always lost to heat. Also, a system cannot convert all of its energy to work in energy. The second part of the law is more obvious. A cold body cannot heat up a warm body. Heat naturally wants to flow from warmer to cooler areas. Heat wants to flow and spread out to areas with less heat. From the two equations above, we can see that if an engine is reversible, it satisfies the following relation. And rearranging slightly, we can rewrite this as follows. This quantity, Q divided by T, is the same for both reservoirs, and is defined as the change in entropy. The change in entropy of a system is equal to the energy flowing by heat into or out of the system as the system changes from one state to another by a reversible process divided by the absolute temperature. Entropy has units of joule per Kelvin. Let's now apply the definition of entropy change to the case of a reversible heat engine. First, heat leaves the hot reservoir. Thus, the entropy of this reservoir decreases by the amount of heat divided by the temperature. Since that is the magnitude of the heat leaving the hot reservoir, we use the minus sign to indicate a decrease in entropy. Similarly, heat is added to the cold reservoir. Hence, its entropy increases by the amount of heat divided by the temperature. The total entropy change for this system is given by the equation. It follows that the total entropy change vanishes. In other words, the entropy does not change in a reversible engine. But no real engine processes are reversible. But a real engine will always have a lower efficiency than a reversible engine operating between the same temperatures. In other words, no real engine is reversible. This means that in a real engine, less of the heat from the hot reservoir is converted to work. Hence, more heat is given off as waste heat to the cold reservoir. Thus, for a given value of heat from the hot reservoir, the heat of cold reservoir is greater in an irreversible engine than in a reversible one. As a result, we have more entropy of cold reservoir than the hot reservoir. Therefore, if an engine is irreversible, the total entropy change is positive. In other words, the entropy change increases. In general, any irreversible process results in an increase of entropy. Since all real processes are reversible, the entropy of the universe continually increases. Since all real processes are irreversible, the total entropy of the universe increases whenever an irreversible process occurs. Mathematically, we can write the following equation. Now let's see how it works. We first calculate the entropy change of the hot reservoir. As the heat leaves the hot reservoir, its entropy decreases. We now calculate the entropy change of the cold reservoir. When the same heat enters the cold reservoir, its entropy increases. We now sum these contributions to obtain the entropy change of the universe. Let's see another example. The energy needed to melt the ice is the mass times the specific latent heat of fusion. Ice melts at a constant 273 kelvins. So the gain in entropy of the ice is given by the room transfers the same amount of heat to ice melts. So the loss of entropy by the room is We now sum these contributions to obtain the entropy change of the universe. Let's see another example. The heat transferred by the warm water is the same as the heat absorbed by the cold water. The gain in entropy of the cold water is the loss of entropy by the warm water is. We now sum these contributions to obtain the entropy change of the universe. Let us think about the result. First, why has entropy increased? Mixing the two bodies of water has the same effect as the heat transfer of energy from the higher temperature substance to the lower temperature substance. The mixing decreases the entropy of the hotter water but increases the entropy of the colder water by a greater amount, producing an overall increase in entropy. If the process is irreversible, then the total entropy of an isolated system always increases. Second, once the two masses of water are mixed, there is no more temperature difference left to drive energy transfer by heat and therefore to the work. The energy is still in the water, but it's now unavailable to do work. Entropy also describes how much energy is not available to do work. The more entropy, the less of a system's energy is available to do work. Third, the mixture is less orderly, or to use another term, less structured. Rather than having two masses at different temperatures and with different distributions of molecular speeds, we now have a single mass with a broad distribution of molecular speeds, the average of which yields an intermediate temperature. These three results not only are related, but are in fact essentially equivalent. Heat transfer of energy from hot to cold is related to the tendency in nature for systems to become disordered and for less energy to be available for use as work. So what determines the direction in which a process spontaneously will go under a given set of conditions is the entropy. To illustrate this, look at the figure. If the particles represent the gas molecules at normal temperatures inside a closed container, which of the illustrated configurations came first? One of the ideas involved in the concept of entropy is that nature tends from order to disorder in isolated systems. This tells us that the right-hand box of molecules happened before the left. Since entropy gives information about the evolution of an isolated system with time, it's said to give us the direction of time's arrow. If snapshots of a system at two different times shows one state which is more disordered, then it could be implied that this state came later in time.